My name is Joseph Derenthal, and my presentation is on aerogels. So aerogel is a super light and highly porous solid. It's derived from gel. And the way that light kind of scatters throughout the structure of aerogel, it causes this translucent, hazy blue look that you saw in the first slide. And this appearance has led aerogel to often be referred to as frozen smoke, which I found pretty interesting. And the porosity of aerogel, it's over 90%, and a lot of times it is over 95%. And the refractive index is about 1.05, which is very low. Silica aerogel is the most common form of aerogel right now, and the density of this can really be anywhere from like 1 to 500 milligrams per centimeters cubed, but it typically falls right around 100 milligrams per centimeter cubed. Another form of aerogel is graphene aerogel, which is actually right now the least dense solid that we know to exist. And the recorded density of that is about 0.16 milligrams per centimeters cubed. And for reference, the density of air is about 1.2 milligrams per centimeter cubed, which would make graphene aerogel have a density about 7 times lower than air. But what I found super interesting about aerogel is how it's the super light material, super low density and all that, but it's still an extremely effective insulator. So the first thing that has to be done in order to make an aerogel is to start by forming the gel by combining a polymer with a solvent. And then after that, the liquid is just removed and replaced by air. And it sounds pretty simple, but it's a little harder process than that, obviously. And the method on the right shows a way of using supercritical drying to replace the liquid with air. So aerogel obviously has a very unique structure, and while its solids are very good or very poor conductors, over 90% of its volume is just air. And this air is trapped within like these microscopic pores that are formed by the solids. Since the air is trapped, it has really nowhere to go, nowhere to move, which almost completely inhibits both convection and gas phase conduction, which is really what makes aerogel such a good insulator. And on top of this, aerogel also has very high load bearing capabilities, despite its pretty low weight, actually extremely low weight. So aerogel is still being tested for its use throughout a few different industries, but one in particular that is kind of leading the charge and has pretty strong potential for near future use of aerogels is the astronautical industry. So NASA in particular has been performing a good amount of scientific research about aerogel and how they could possibly use it. One of the things that they found is how silica aerogel is pretty ideal for storing liquid helium, which they obviously use for cryogenic cooling. And then another thing that NASA has researched is the Mars mission EVA suits for astronauts when they eventually travel to Mars. And really the only thing that they found close to meeting their insulation needs for these suits has been aerogel composites. Another field conducting research right now regarding aerogels is the biomedical field. Although it is still somewhat limited compared to the astronautical field, they've shown some studies have shown that aerogel could cause benefits in oral drug delivery and how rapid it is absorbed, as well as cardiovascular devices such as engineered heart valves, which could have potential for future medical usage. And one more thing that aerogel is kind of being researched on right now is how it could be used to help with medical or nuclear waste and nuclear storage. And their method that they have kind of laid out and that they would like to use for this is just soaking the aerogel within the radioactive waste in a radioactive solution, which will cause the solution to kind of go up into the aerogel and get trapped where the air typically gets trapped. And these are my references. Thank you.